לבד. לשבת בשקט, זה עובד. שלום לכולם וברוכים הבאים ליום בן-תור, כי יש לנו, נקרא ליום, כי יש לנו כמה וכמה דברים. חלק מהדברים שאני אעשה, some of the things I will say will be in Hebrew and some will be in English. You'll excuse me for... מול המצלמה, אמרו לי להיות מול המצלמה, לא רגיל. היום הזה נעשה תודות לניווטה של פרופסור מרים קסנר, שגם תורמת את הפרס, והנוהג שלנו הוא להביא מרצה מחול ליום הזה, ולתת את הפרס שנתרם. אני אקצר בדברים כי סך הכל הזמן כבר רץ, ואני אבקש קודם כל מישהו לספר לנו על בן-תור, למרות שהוא אומר שהוא מתחיל לסרב שנמצא מישהו אחר ודור חדש. אז הוא אמר לי ככה, אבנר איילון, שנה הבאה, נדבר. הוא התחיל לתת לי רשימה. אז מישהו בבקשה. רגע.
You'll excuse me, I'll speak in Hebrew to the Israeli audience. הייתי רוצה לקוות שלגיאולוגים שבינינו, גם לצעירים ביותר, אין צורך לספר מי הוא בן-תור. זהו בן-תור ממפות הנגב, בן-תור ופורמן, כולל המפה הקלאסית של גיליון סדום, בן-תור ממפות סיני, בן-תור מהעבודות הראשונות על ים המלח, בן-תור מהעבודות הראשונות על חפרורים, בן-תור מגלה שדות הפוספטים של ישראל. יעקב וינטר נולד ב-1910 בקניגסברג, אז מזרח פרוסיה, גרמניה, היום רוסיה, היום זה קלינינגרד ברוסיה. הוא קיבל השכלה אירופית קלאסית, כלומר הוא למד במספר אוניברסיטאות בגרמניה וצרפת, משפטים, בלשנות, פיזיקה, היה איש משכיל מאוד. ב-1933 עם עליית הנאצים הוא עלה לארץ, החליף את שמו מקורט וינטר ליעקב בן-תור, והצטרף לפיקארד בבניית המחלקה לגיאולוגיה. באמצע שנות ה-30 נסע לצרפת להתחיל דוקטורט על הסלעים הוולקניים של הפידדום במסיב סנטרל. הוא סיים את העבודה אבל לא הספיק להגיש אותה כי פרצה המלחמה, והוא חזר לארץ. התחיל דוקטורט חדש על הדולומיטים של קריית ענבים. השלים את זה, היה לדוקטורנט הראשון של האוניברסיטה העברית בגיאולוגיה. בתחילת מלחמת השחרור, בן-תור גויס על ידי פרופסור ישראל דוסטרובסקי למה שקראו אז חמ"ד, חיל מדע. הצטרף עליו אז מי שהפך לחברו לכל החיים, עקיבא פרומן, שעלה אז מהולנד, קצת לפני זה. יחד החלו, הם היו צריכים למצוא, המשימה שלהם הייתה למצוא אוצרות טבע, בעיקר אורניום חיפשו, נפט ומקורות מים בנגב. ולצורך זה הם התחילו במיפוי גיאולוגי של הנגב. הלכה איתם חבורה שלמה של אוהבי טבע, בעיקר בוגרי מחלקות הסיור של הפלמ"ח, שכל אחד מהם השאיר אחר כך חותם בתחום שונה לגמרי של מדעי הטבע. היה ישראל זק, רובם כבר לא בין החיים. היה ישראל זק שאחר כך המשיך בגיאולוגיה ועשה את המפה הנפלאה של הר סדום, את העבודה הנפלאה על הר סדום. דני זוהרי שהיה לבוטנאי מוביל, יעקב ורמן שהיה גנטיקאי, פרופסור לגנטיקה, ויבדל לחיים ארוכים אביתר, אייבי, נבו, שהיה גיאולוג מצטיין, והיום הוא פרופסור לאבולוציה באוניברסיטת חיפה. כל אלה הלכו אחרי בן-תור במיפוי הנגב, כהלוך הילדים אחרי החלילן מהמלין. אחרי מלחמת ששת הימים, בן-תור, יחד עם מושי אייל, התחילו במיפוי סיני, ומיפוי חלק גדול, לא פרסמו את הכל. בן-תור נתמנה לפרופסור באוניברסיטה העברית ולמנהל המכון הגיאולוגי. כאן הדריך רבים מבני הדור שהיום הם זקני הפרופסורים של המחלקה הזאת. בעבודות המאסטר והדוקטורט שלהם. את איתן סרס, את צבי גרפונקל, את עמיתי כץ, את סטארי, אותי. ודאי שכחתי כמה. במידה רבה מאוד, בשנים ההם בן-תור קבע את פרצופה של המחלקה לגיאולוגיה לשנים רבות. הוא היה האיש עם הכריזמה הבולטת ביותר שאני הכרתי. הוא לא היה מלמד, הוא לא היה מורה טוב. או שהוא היה מורה אבל לא מלמד. הוא ידע להעביר שיעור שאחריו חשבת שכרגע שמעת את הדבר הכי מרתק בחיים. ורצית ללמוד עוד. היו שנים ומחזורים שבהם בן-תור לימד כמעט הכל. מינרלוגיה וקריסטלוגרפיה, פטרולוגיה מגמטית ומטמורפית, גיאוכימיה. הוא גם הדריך את הסיורים בנגב, ברמון, באילת. סיורים שתמיד נמשכו עד חשיכה, והמחשוף האחרון היה נבדק לאור הפנסים של הג'יפים. היה לו כושר ניסוח מעולה. אף כי העברית לא הייתה שפתו הראשונה, הוא כתב עברית נפלאה. מי שרוצה לראות את התוצאות, מי שעוד יש לו גישה לדבר העתיק הזה ששמו האנציקלופדיה העברית, יחפש כל ערך שקשור בתחומים שהזכרתי, ועל מרבצי בצרים באנציקלופדיה העברית. הערכים האלה כתובים על ידי בן-תור, מופת של כתיבה מדעית פופולרית, מדויקת ומנוסחת יפה. בהירה. תלמידתו רעייתו של בן-תור, פרופסור מרים קסטנר, היא שתורמת מדי שנה את הפרס לעבודת דוקטור מצטיינת על גיאולוגיה של ארץ ישראל. כמובן שכולנו מודים לה על זה, ואנחנו נעבור לטקס.
אז כמו שישו אמר, מדי שנה אנחנו מעניקים את פרס בן-תור, והשנה שולחים אותי לתמונות, להצטלם. והשנה חתן הפרס הוא שחר שני קדמיאל, באוניברסיטת בן גוריון, הוא נמצא כרגע בהולנד, אבל הוא הגיע לפה.
נמצא כרגע פה.
אני יודע שהוא נמצא כרגע פה. חכה. שחר נבחר מבין 3 מועמדים שכולם מעולים. אני קורא כתב הוועדה, אני לא הייתי חבר בה, מה שקשה עליה את משימת ההחלטה הזוכה. תחום המחקר של שחר הינו קריטי להבנה של סיכון הסייסמי בישראל, אשר גבולה המזרחי הינו גבול טקטוני פעיל. למרות רקורד היסטורי, ארכיאולוגי וגיאולוגי של רעידות אדמה הרסניות, מדידות מודרניות של רעידות חזקות לא קיימות בישראל, בעיקר מכיוון שמאז הוקמו בארץ תחנות המדידה לא התרחשה רעידה חזקה שימשך ככה. בהיעדר תנודות מדודות הסתמכו מחקרים והערכות עד כה על שיטות אשר פותחו ונבחנו באזורים אחרים בעולם, למרות שמידת ההתאמה לישראל אינה ברורה. מחקרו של שחר מגשר על פער מידע זה באמצעות סימולציות של רעידות אדמה וירטואליות עבור המבנים הגיאולוגיים בישראל. דגש מיוחד במחקרו של שחר ניתן להבנת תנודות קרקע באגנים סדימנטריים עמוקים המלווים את בקע ים המלח ומבני שבירה סמוכים. באמצעות המודלים אשר שחר פיתח, ניתן יהיה לחקור רעידות אדמה היסטוריות ולנסות ולדמות רעידות עתידות כדי להעמיק את הבנתנו בנוגע לסיכון הסייסמי בישראל. תרומתו של שחר מתבטאת בהבנת תהליכים בסיסיים המשפיעים על תנודות הקרקע, תוך כדי מעבר הגלים דרך מבנים גיאולוגיים מורכבים. למשל, אפיון הגברת תנודות בקרבת קצה אגן, באזור תשתית כמורה או כעורה, ובסופרפוזיציה של מספר גומרים שביחד יוצרים אפקט מורכב ומסובך. שחר פיתח לא רק את התשתית המחקרית הנדרשת למחקרו, אלא הקים פיזית את התשתית החישובית הנדרשת לביצוע המחקר. בנוסף למחקרו החישובי, שחר תכנן, התקין וניהל את המערך הסייסמי הנייד אשר הותקן על ידי המכון הגיאולוגי בעמק זבולון. מערך זה תוכנן לספק מידע אודות תנודות הקרקע בעמק ואת ההגברות הצפויות של תנודות אלו על סמך מדידות של רעידות אדמה קטנות. גם במקרה זה, זהו המחקר הראשון מסוגו בארץ. לסיכום, שחר תרם תרומה מכרעת לפיתוחו וביסוסו של תחום מחקר בנושא תנודות קרקע בישראל. על הישגיו אלו אנחנו מעניקים לשחר את פרס בן-תור לשנת 2017, על החתום, ועדת הפרס, אלן מתיוס, ארי מטמון ורון שער. עכשיו אתה יכול לבוא. זה התעודה, ואתה רוצה להגיד כמה דברים, אני מניח, קצר.
I'll speak in English. Dear friends, esteemed colleagues, Professor Claude Jaupart and Professor Miriam Kastner, I'm honored to be here and grateful to be the recipient of this award. To be considered for the Bent-Or Award is a great honor and a privilege. Yaakov Bent-Or was one of the founding fathers of earth sciences in Israel. As an undergraduate student, I remember his name come up at pretty much every stop, at every field trip, in papers that we had to read in preparation for exams, in the classroom. And we used to joke among ourselves that there is no way he did all of that. I didn't know Professor Bent-Or, but I knew and loved my grandfather, who also immigrated from Russia in those days and helped build moshav after kibbutz in this country. And I used to listen to his stories and think there is no way he did all that. But they did. They belonged to a generation that worked hard and knew no rest. The professors, the old professors of today, as Yoshua said, most of whom were students of Bent-Or, say that he was a fascinating teacher, and that they used to joke that he could fascinate his listeners even by reading out loud a phone book. I also heard that Bent-Or was the first person to be awarded the doctoral degree from the Hebrew University. Well, I can tell you that in my family, I was the last one who anyone thought would be a doctor. I was the weird one with the interesting rock collection. And this is something I think I share with a lot of people in this room. I'm currently a postdoc fellow at Delft University of Technology in the Netherlands. I'm using signals from earthquakes, volcanic eruptions, explosions, landslide, glacier calvings, and other passive sources in order to probe the upper atmosphere and the deep oceans, where in situ observations are very rare and satellite and other remote sensing techniques are hardly applicable. I'm also continuously developing ground motion prediction models for the Dead Sea transform and planning to continue doing so upon my return to Israel. I stand here today humbled by the occasion, grateful to all the people who have helped me get here, my teachers, my PhD advisors, Zohar Wirtzman, who is in this room, and Mikael Sasarsky, who is guiding a field trip today, For all the support that they gave me along the way, they continue to look after me even today. To my fellow scholars, all of you, for making their contributions to this engaging environment, and many, many more. I would like to thank the selection committee that found me worthy of such an honorable award, and by doing so, allowed me to join a list of respected scientists that have won this award before me. Thank you very, very much.
Okay, Shachar transformed us to English, so let's stay in English. Is that okay, Claude? My job is to introduce to you Claude Jaupart. Many of you came across the name, and but still, I try to squeeze some Vita data from Claude before the talk, and it's very hard. He didn't want to release much, so he only was willing to say that he started in mining engineering. This was his first degree in France, and in a hope to work on geothermal energy. He couldn't find anything interesting at the time in France, so he went to the US and got a PhD there. And then he got interested in the thermal structure of the planet. So just a personal note, I asked him which year, he said 82, and just a year after I started my graduate school at California, and already Claude Jaupart was a name that we were learning in the courses. You know, it was like coming up as a classical. So 10 years later, when I ran into him, actually Oded Navon introduced us in a conference, because the guy they were all already, both of them, engaged in volcanics and magmatic process. So I was surprised to see a guy of our age, very well accomplished, and then, so I asked him, but you were, I asked him now before the talk, I remember you were head of Institut Physique de Globe de Paris. He said, yeah, I did that too, a little thing. Between the two terms that he was a chairman, I managed to visit him to get some work together. I was hoping he's not too busy now because he's off the duty, but then we had a nice plan to work on stretching, etc. But I couldn't talk to him because everybody was pouring in from the Institute and from Paris to congratulate him. He was elected to the Academy of Science, the French Academy, and he keeps saying, no, it's nothing. Let us try and work, but we couldn't. So maybe now. So anyway, I'm really pleased and honored to have you here. Go ahead.
Toda Amot, I know only two Hebrew names, so Shalom and Toda, so that's got to do with this. It's a great honor for me to be here. I read, of course, about Yaakov Ben-Tor's career, and he's obviously a larger-than-life person. I realized that he did some of his studies in Paris, so he must have spoken French. But then, of course, he got involved in the creation of the State of Israel and generated the whole of the Israeli, I think, geological map and the whole of the Israeli geological community. So a larger-than-life person, and that's for me quite difficult to measure up to him, but I will try. I was told to give a lecture that would appeal to the general audience, so some of you may be a bit bored by some of the stuff, but I made a general introduction to the topic. And in the honor of Ben-tור, I wanted to show that you can approach geological problems in many different ways, and in many cases, this variety of approach is absolutely necessary. And I think that, for example, from what I know about the work here and the work of Amos and the work of Oded, this is very much the way people approach the problem, and I think that's the right one. So I will tell you about the continental crust. This was not done on my own. I had many students and colleagues, and so this definitely was not done in isolation. Okay? Claude. If I can. Okay, so the Earth is made of, the first thing that you'll notice if you come from outer space is that the Earth is made of continents and oceans. These are very different domains, and continents stick out. Their topography highs. The oceans, of course, are different beasts. And there's several things about the continents that require attention. First, they're obviously standing high, so they're not made of the same material. They're made of buoyant material. Second thing is that they're old. They're much older than the oceans, and some of them have resisted the whole of geological perturbations throughout several billions of years without being very much perturbed. So they're old, sturdy, stable, made of buoyant material. So this is the several things that are deal with their basic structure. The other thing is that they form huge masses. So to form a continent, it's just only to form the material, but it's also to make sure you understand how you generate these large land masses. So basically, there's the idea that the continents are kind of a foam that floats on top of the Earth, but that's of course a very small part of the problem. To understand how continents form, it's first a chemical petrochemical problem. How do you form the foam? How do you extract it? How do you segregate it to the top? It's also a mechanical problem, because how do you segregate to the top? And you'll see that it's a two-way process. Not only do you have to get something to the top, but you also have to return some things down below, otherwise you would not isolate the crust as we know it. It's a thermal problem, because none of this could happen if everything was cold. Earth materials that are cold do not deform, do not allow motion very well, so there's a thermal problem there as well. And it's a geological problem, because you have to form these huge land masses, and how do they get formed? How do they get assembled? So I will broach some of these topics, because throughout my research I've touched upon these things. There are bits that are missing, and then we can discuss them later on. But I will try to see that you need to get to the problem using all of these questions. First, the chemical petrochemical problem. If you look at a very simple chemical diagram, let's say you wait as silica on one axis and say magnesium on the other one. We have two basic fields, the basalt, which are the main liquids that we will work with, then the continental crust. And the key question is, how do you go from basalt to continental crust? Then there's granite. In the old days, it was quite clear there were a lot of granites in the continental crust. And so granites are an essential part, but you can see that the continental crust as a bulk is not only granite. So how do you go from basalt to the bulk continental crust? Well, the first thing that we know is that if you let the basalt undergo fractional crystallization, you will generate granite-type liquids. But of course, this is not the end of the answer. As you can see, this field is not going through the bulk continental crust field. But the other thing, of course, is that if you just segregate granite and leave the residue in situ, then you will not have changed the bulk composition. So somehow we have to get rid of mafic cumulates that form when basalts crystallize. So this is why it's a two-way process. Not only have you got to form evolved silica-rich melts, but you also have to get rid of the mafic cumulates. Otherwise, you would not change the bulk composition. Then once you have formed basalt, granite, and you've gotten rid of the mafic cumulates, then you can mix the two in various proportions, and you will get to the bulk continental crust field. So I will, the first part of the talk, I will talk about the problem of mafic cumulates and how do we get rid of them, and do we have evidence for this. That's purely a chemical or petrochemical point of view, but what is the physical mechanism by which we get rid of these mafic cumulates, and do we have geological evidence for it? So if we look at the way magmas will move and will eventually stall at somewhere in the Earth, we have to look at density. Everything is driven by buoyancy in the Earth. So that's a plot of density and depth. The solid black line is the bulk continental crust field. And this is the basalt for dry. This is the curve for dry basalt or for basalt with water. And you can see that if you take dry basalt, the basalt will be buoyant with respect to bulk continental crust until some intermediate depths in the crust, above which it will be denser than the local crust. Of course, buoyancy will not be able to carry the basalt much further up. If it is water rich, it will be able to make it. But of course, near the top, there's usually sedimentary rocks and molluscs. So the first story is that indeed basalt will segregate to the top as the form that I showed in the introductory slides. But in most cases, the basalt will stop before reaching the surface. And we can see examples of this. And I will draw from the field because, of course, that's in geology. You always have to go back to the field. And let's look, for example, at the Rum intrusion in Scotland. Rum is here. It's an island away from the western coast of Scotland. Beautiful island with beautiful mafic rocks that are exposed. And if you look at the cross structure through the Rum, this is the Rum layered series. This is a fascinating petrological set of rocks that have spurred a lot of studies about the way magma is crystallized. And you can see basically the way this unit was able to rise and get stuck near the surface, because the initial density of this melt was about 2.6, and it got stuck against Mesozoic sedimentary rocks that are less dense, and so of course the basalt could not make it through. You have also an intimation about the way the basalt was trying to push its way up to the surface. That's fine. Basalt is also very much denser than the Lewiston basement there. But if you look at the deeper structure of the intrusion, there's something that is bizarre. It is underlain by this very thick root. And so that's a big question. What is this root meaning? If the basalt was able to rise, why you have this thing here? So that's a bizarre thing. If you look at another set of intrusions, that's a fascinating one. It's the Great Dyke in Zimbabwe. So that's a satellite image. So that's the boundary. I didn't choose this because of the recent unrest in Zimbabwe, but that's a sort of fascinating geological structure. So that's the Limpopo belt, which separates the Zimbabwe craton from the South African craton, or the Kalahari craton. And that's this huge thing, which is about 550 kilometers long, a very nice and beautiful intrusion, basaltic initially, and clearly a very, very big intrusion. So basalt was able to make it quite close to the surface. But this internal structure is again very bizarre because it has this funnel-shaped structure with the layering that has been deformed this way. And we'll come back to that later on. This funnel shape is quite a common feature of these type of intrusions. Usually been attributed to the input of magma from below, but it doesn't fit the evidence. First, because if the funnel was the in-placement structure, this would have meant huge flow rates. And the other thing is that the layering is discordant in many places, so it doesn't fit this type of model. So again, there's a bizarre structure there. And if you look at still even bigger intrusions, so that's the Great Dyke over there, the Limpopo, which separates the Zimbabwe and the South African craton. You can see this huge mass here, which is a bushveld intrusion. That's again a basaltic intrusion, very much larger. That's the geological map. You can see that it stretches across about 350 kilometers. Huge structure, which has irregular features. It's not nicely drawn as the Great Dyke. It's not as nicely round shaped as the Rum intrusion. It has a more complicated shape, and it's even more bizarre when we look at cross sections. I will show you two cross sections to that body. It's been extensively studied because it hosts most of the Earth's platinum. So that's two cross sections across the bushveld, and the igneous series, which are essentially now mafic cumulates, are in green. You can see the structure again stretches across about 350 kilometers, but you can see how irregular it is. And in some places you're missing completely the mafic cumulates, they're gone. And it's clear that they were there. In some places you have very little left, in some places there's nothing left. And you can also see the very irregular shape of that intrusion. So these are puzzles, and I think what I want to try to convince you of is that these are indicative of the delamination of mafic cumulates. It didn't go to completion in these cases, and we can understand why. And so I think these intrusions provide evidence for the phenomenon that I told you before was essential to the generation of continental crust. These things happen, they did not go to completion there, and hence the bizarre structures of these intrusions. To understand why there are things that have got to happen to these intrusions, there's a major density change upon crystallization. So let's go back to the rum, that's temperature and density. And if you look at the rum composition, the rum initial melt composition, which you can retrieve from the chilled zone that are at the edge of the intrusion, you start the liquid which is about there. And of course you can see here that we've plotted the density fields for the shallow sedimentary layers, the Lewisian basement below, and you can see that this melt density was of course less than that of the Lewisian basement, so the melt was able to rise. And that's fine, but then it started to, it got in place at the interface between the two, and then it started to crystallize. And when it crystallizes, the density goes up like that. Now, density of phenocryst or bulk melt follow the same trend. There's a huge density change upon crystallization. And if you look only at the mafic cumulates, you've got this enormous density there, and this is what is left now in the above intrusion. This is also why there's a huge gravity anomaly above that intrusion. So there's a huge density change upon crystallization, absolutely enormous. So what drove the magma to get in place? Of course, once the magma started to crystallize, the whole forces that were involved in the structure changed. You can see this in many other places, just a few big intrusions. The rum I've mentioned, the Bouchevel, the Sept-Îles is a very major intrusion in the St. Lawrence River in Canada, in eastern Canada. And if you compare the host rocks and the magma, that's the initial magma. You can see usually the magma is buoyant with respect to the rocks, or the crust. But then if you look at what's left, the mafics that are open today, then this density is very much larger than those. So there's a huge change in the density structure of the intrusion as it crystallizes. There's a buoyancy reversal, and of course, that's the kind of phenomenon that we want to study. So we have to look at two different processes. One is the in-placement process, which is such that the magma come in, it's buoyant with respect to the underlying rock, it's negatively buoyant with the upper layer of central rock, but then as it crystallizes, it's denser, then it will start to sag and founder. Two very different processes driven by two completely different density values. Do the country rock deform? Yes, because there's a huge driving stress here. You can estimate the stress without sophisticated models for what happens, just simply by looking at the buoyancy. We know the density difference, and we know the thickness of the units. And basically, what you can compare, you can set this into the equations for the rheological behavior of country rock. Then you'll find out this country rock will deform very significantly with such stresses. And the strain range will be much larger than 10 to the minus 13 second minus 1. And let me remind you that for tectonic fields, we usually consider stresses of about 10 to the minus 15 or something like that. So what you have here is very large strain range that are able to deform rocks very significantly. So the country rock is able to deform with stresses that are available. You can say this in terms of viscosity. So, of course, temperature is a key issue here. If I've taken here three different types of rheological equations for crustal rocks with that type of driving stress as a function of temperature, and obviously the hotter the rock, the easier it is to deform. So you can see, therefore, this big effect. You can see there's going to be a problem by having very exact models because of this change of rheological behavior if you go to granite or diorite or whatever. So that's always going to be a problem when you make mechanical models for the Earth's crust. Geology is made of heterogeneous material, and so that's why we always have to go back to the field, because you can't be certain that it's the best strategy to model crust as quartzite, for example. But we have to remember two basic things. One is that given the stresses that are available, there will be deformation, and the deformation will be very sensitive to temperature. Now, I think the best evidence we can find is by looking at the structures. So I've shown you how these intrusions are shaped today, and the question is, can we account for these shapes? So I think the shapes, the patterns, and that can be done by geological mapping, provide very strong evidence for what's going on, regardless of complicated theoretical models. So let's look at the emplacement process. So what we have is magma that's coming in. It's buoyant with respect to the lower layer of the crust, and it's negatively buoyant with respect to the upper layer. So it gets in place at the interface between the two, and it will spread. And depending on how it spread, it will generate different conditions for what happens afterwards when it becomes dense. So that's why we can't study foundering, this late phase I was mentioning, without understanding the first phase. So let's look first at the first phase. And to look at what happens, we did this in the laboratory. These are very tricky experiments. So you have to generate a fluid which will get in place between two layers. And the trick is to find a fluid that will be initially sandwiched between the two fluids here, but then it will become denser than these fluids when it cools down. There's going to be no crystallization, so this is not an exact duplication of geological reality, but it will tell us about the kind of shapes and patterns that can form this way. So we're going to inject some finite volume of fluid in between these two layers, and this fluid will cool because it's against other fluids that are colder than him, and we'll see what goes on. So the laboratory setup is very easy, but the trick is to prepare the fluids. And so we have cameras. The tank is here. It's about 13 centimeters high, 30 centimeters wide, and we control, of course, temperature, volume, fluid properties. And I'm going to show a few movies about what's going on. So let's look at the simple one simple experiment here. Now we inject the fluid. It will spread at the interface, but as it spreads, of course, it cools down. You can see it spreads, but eventually it becomes denser, and then it starts foundering. Now the density changes are a few parts per thousand, so it's a very tricky set of experiments, but everything's still well controlled. So you can see the two very different type of behaviors there. And I won't bore you with fluid mechanics, but just to give you an idea of what's going on, this is a well understood process. So we're spreading, we have to deform the density interface, we have to deform the fluid above, the fluid below. So there's going to be two different properties, densities and viscosity involved. And basically what's driving everything is buoyancy, and the buoyancy force is resisted by shear at the top and bottom of any intrusion. And what we're interested in is how far does the emplacement proceed, what is the large dimension of the intrusion, what's its aspect ratio. And so we understand how these things evolve. And the critical thing is that, of course, as it stretches, this intrusion, then it becomes much harder to stretch it further because you're trying to thin a fluid layer, so viscosity will act against this. You just can't stretch a very thin layer of fluid. And at the same time, cooling becomes more and more efficient because you're cooling something which is thinner and thinner. And so basically, everything will be determined by the competition between the rate of cooling and the rate of spreading. And so you can work out the time at which the end of spreading will occur, simply when the spreading rate will become less than the cooling rate. And so I'm not going to give you the detailed theory, but basically you can work out what the aspect ratio of the intrusion is, the thickness of the radius, and you can show that it's given by this parameter AI, which looks like, for those of you who understand and like a convection phenomena, it looks like a Rayleigh number. This thing involves all the densities, but the important thing you can see here is that this parameter here is proportional to V. So the larger the volume, because it's carried to the power 1/3, the smaller the aspect ratio, the thinner the intrusion. And of course that fits the geological record very well. And this is all the experiments that we've been able to do. There's 12 of them. And that's the aspect ratio when spreading ceases against that number. And that's this theory that I was showing you. So it's reasonably consistent with the experimental data. So what we know here is that basically, the larger the volume, the laterally more extensive the intrusion. Now, what are the consequences for what happens afterwards? Now we've got this intrusion, it spreads, and then it starts to crystallize, becomes denser, and become free rocks. And then, of course, the foundering will start to occur. And we found 3 different regimes of foundering. The first one I've shown you in my previous movie. You saw this thing, and from the drop, that's the drop. But when you have very small aspect ratios, something else occurs. And I will illustrate this by this movie. So that's one movie. So you have the side view and the view from above. That's what we call the annular regime. What you've done is you thin, I will play it back. You thin the intrusion at the center and you thicken the lobes, and you generate lobes at the edges. And so that's the remarkable thing. You see how it spreads, and then it starts to founder, and you've basically depleted all of the central part of the intrusion, thicken the edges, and then these go down. So that's what we call the annular regime. And the other regime is even more fascinating. Same thing again. And then you find these, what we call the jellyfish structure. You have these instabilities that occur within the central part of the intrusion. Now, this thing is probably not realistic for layered intrusions or for intrusion in the Earth, because it requires a specific viscosity ratio. But what these experiments tell us is that the shape of the final intrusion is a result of 2 different things: emplacement and then the foundering. And the foundering will, of course, proceed in different ways depending on this emplacement phase. The other thing that it tells us is that the shape of these things can be quite complicated. You will not form a single set of intrusions, regardless of volume, regardless of viscosity. You will generate different types of intrusion depending on the volumes and the viscosities. So these are the 3 foundering regimes that we found: the drop, which is the one I iterated, this annular regime, where you thin the central part of the intrusion, and the jellyfish, which has the thin central part, but also this kind of lobes. Now, if you remember what I've shown you about the rum is strongly indicative of this. And the Bushveld, if you remember, and maybe also the Great Dyke, we'll come back to that later on. The Great Dyke is also indicative of this regime. And the Bushveld, this very large intrusion in South Africa, is probably somewhere in between these 2 regimes. Clearly, we have a thin central part. In some places, we don't have anything left. In fact, no accumulates that are left, no mafics left. And these very irregular structures, and also this very lobate type of structure that we see in the horizontal cross section. And of course, the boundary between these 2 regimes is a question of aspect ratio. If you have a very thin and large intrusions, you will favor these annular or jellyfish type of instabilities. And if you look at the aspect ratios, again, the geological evidence is consistent with that. For the rum intrusion or the Great Dyke, they're in this field, and the Bushveld is in that field.
These are the experiments or the observation in nature?
That's the experiments, but we predict these shapes depending on these aspect ratios, and it's consistent with what we see in the field. But that's derived from experiments, and then we compare with the field, we know the aspect ratio, and then we can find out whether it's consistent or not. Is that it? Okay, so basically what we've learned is that the second phase is quite, can have various shapes. There's a sequence of increasing deformation with increasing volume. That's not really surprising. Increasing volume means an increasing force available. There's a sagging, which is the smallest intrusion will just barely sag. A funnel structure. This is the kind of structure that we saw, for example, in the Great Dyke. And then if everything's hot, then sinking. And then in some cases, I won't show you the experience, but you can lose everything because everything is hot and everything goes down. There's nothing that is left at the surface. And of course, we have a complex shape for small aspect ratio, thin and wide intrusions. So we expect thin and wide intrusions to have a complicated structure. Now, of course, as you saw in the field, we don't proceed to completion. We are left with some of the mafics. So to find out exactly how this occurs, you can't do this in an experiment. We didn't find the right fluids to be able to do that. So we went numerical. So basically, we start with the same type of structure. We have an initial intrusion. We start the calculation at the end of the emplacement phase. And then we have nonlinear rheologies and also temperature-dependent rheology. What this will allow is that basically the intrusion itself is carrying a lot of heat. It will heat up the country rock, so it will make deformation easy. Then, of course, with time, everything cools because the intrusion loses heat to the surroundings. And eventually, the surroundings are not able to deform because they're too cold. But yet, they're still able to withstand the load because we have still these dense cumulates. They're still there. And of course, they will be able to stay there if the country rock can sustain the load. So I'll just show you one set of experiments. As I told you, we can do all the numerical calculations we want. Now the computers and the codes are robust. There's no problem with that. The key question to go back to the field is that we just cannot make sure that we can be sure that we have the right rheology. It's not clear what is exactly the rheology of crustal rocks. So there's always going to be a competition between temperature and rheology. You can choose crustal rocks that are weak and they will deform even at reasonably cold temperatures, or you can take crustal rocks that are quite strong and they will only deform at high temperatures. So there's always this competition between temperature and strength. But basically what we find is that if you do these calculations, that's for reasonable conditions for the crust. Now you have depths in kilometers. It's not in centers like in the lab. That's the temperature field. And you can see we chose an experiment which would, I think, be consistent with the Great Dyke. First, because it's in 2 dimensions. And you can follow the layering. And here, that's the intrusion in 9 meters. Nothing else happens. The intrusion gets stuck in that funnel-shaped structure. So you can indeed preserve an intrusion that is starting to deform, and then the deformation will stop when everything is cold, and you're left with this kind of structure there. To a blow up of this, if you go back to, if you remember the Great Dyke structure, I think we have exactly the same type of pattern. This interesting set of structures at the edge of the intrusion, and if you're interested, we can discuss that later on. But there's many interesting things we can do by studying the contacts there. So that's the first set of studies that I wanted to tell you about. So we need to have mafic cumulates delaminate to generate the continental crust that we know. And we know how it can work. I've given you examples, which shows examples where, of course, that process did not go to completion, because if it goes to completion, there's nothing left. So we looked at high-level magmatic intrusions, and we saw that their shapes are basically documenting this foundering process that gets stopped before it, and it stopped because these are high-level intrusions. They're in place in reasonably cold country rock, and so there's not enough energy in the structure for this to allow the full delamination. So the study of mafic intrusions allow the testing of conditions that are required for removal. The removal of mafic does not go to completion. And we've got a lot to learn from this. And of course, then the last point is that the ambient temperature when the intrusion gets in place is a very key issue. So I will now go to, because in the honor of Bento, we have to go to the field. And so I will show you that there's things that we can only address by going to the field. Everybody knows that, but something that was remaining. So what I've done as part of my career is go to the field and look at the thermal structure. Everything is eventually boils down to the temperature field. And so what do we know about the temperatures in the crust and elsewhere? So most of my work I've done in Canada, and you can encounter nice animals like that. So that's the second part of the talk. And I will look at the geological problem. What do we know about the formation and stabilization of a new bone continental crust? And one area where I've looked at it is the Superior Province, which is an Archean province in Canada. And then first look at the geology and see what we've tried to document there. So that's the structure of the Superior Province. So we're changing gear completely, and I think that's one of the nice things about the earth sciences, that if you know how to go to the field, you can look at small-scale structures, larger-scale structures. You can't always do this in the same spot, but that's, in fact, one of the good things about geology. You don't get stuck in always the same place. So that's the latest geological map of the structure. The superprovince is this part above the Grenville front over there. So it's the Archean part, and it's made of belts, which have these very bizarre names. So I will give you a few because they're derived from Indian names. So the IPGP, the Wawa, Ketiko, Wabigoon. Now there's English River. There had to be some English people there. I thought it was mostly French trappers, but anyway, there's no French trapper belt. Opinaka and anything like this. So all these are belts. They're made of volcanics and heavily metamorphosed sediments. And the volcanics have got the compositions that are expected for island arcs and volcanic successions attributed to subduction. So what we have is a series of arcs, and I'll show you the timeline later on. And so all these belts were credited to this central core of the craton, which is older, which has a different structure, in fact, which is not as well studied as the southern ones, for simply a difficulty to access to the field, and also the fact that you can rarely have the bare rock at the surface because it's usually buried under snow. So there's this structure here which is older, so you can split the superprovince in two different parts. The southern part is made of these accreted belts, I will show you the timeline later on, and an older core which has a slightly different composition. So what we want to know is exactly what happens when you generate this continental mass. That's a geological problem. You don't only create continental material, you generate a big mass. And how do you generate it? Does it go easily? Over what time scale it occurs? And what happens to temperature? How does the newborn crust evolve? And that's going to be the purpose of this study. So what we know, and I will give you more details later on, is that if we look at the superprovince, we extracted new crust fundamental in island arcs. There's no problem that these were island arcs for these accreted belts. The central core, the older one, that's still up for discussion. Some people claim it's due to some big mantle upwelling. That's not clear yet. But we know there's a big difference between the core and the belts. The belts got accreted to an older core, and this went on through typical geological processes, the welding of belts, thrusting. And there was an interesting thing, there was post-orogenic phases. Once all these phenomena stopped, we had a late thermal phenomenon with high temperature metamorphism and the generation of new plutonic rocks. But the end result is we've got this province which has been there for more than almost 3 billion years without being perturbed by everything else that occurred in this area. And so you were able to generate a very strong and tectonically very resistive piece of continents there. So the timeline, so that's in a million years, so 2.8 billion years, 2.6 billion years. And this is a nice area because there's been a lot of studies, because there's a lot of mineral deposits, there's been a lot of geology made. And I've split these things in different bits. That's the craton core, that's the older one. Then I've chosen these 4 belts to the west and then 1 belt to the east to show you that this is something which is regional. You can see the green, in each one of these plots, at the bottom is the crust building phase, the large volume magmatism that creates the crust. Then this one is the plutonic activity that occurs after this big crust building activity. And then the top line is the metamorphism that is recorded in the rock. And you can see basically here the stories that you've got. You can see there's the timeline here. You go from north to south, you can see these things are getting younger as you go south. As the belts are sequenced like that. There's not much here in terms of crust building because these are mostly metasedimentary belts that were formed probably in basins between the new continents and the belts before it got accreted. So there's not much in these two belts here. And these are the volcanic belts. You can see the nice time sequence here. But you can see that there's time lag between the end of this big crustal building phase and these metamorphic events, which is done everywhere. So what is this telling us? The end of accretion is dated at about this age, everywhere in the province, and the end of any activity is about, so there's about several tens of million years of activity that follows the end of accretion in this area. The end of accretion is 2.6, but there's still activity that goes on after everything got assembled together. So to look at this, of course, this has to do with temperature. So what I'm interested in is to find how I can calculate temperatures in crust. And of course, temperature in crust depends on many parameters. That's the kind of things I will now talk about. But here, the nice thing is that we have evidence for what happens. We have a nice series of dates and a very consistent pattern. So to find out exactly what happens in the crust, you have to find out how much radioactivity is in the crust, because the crust is made of rocks that are enriched in uranium, thorium, potassium. So there's a lot of local heat production. So just to summarize the evidence, we have post-orogenic thermal peak in this area. The metamorphism is high temperature, 8,900 degrees C, moderate to high pressure. So this is something which occurs lower down in the crust. This is something which occurs after accretion. There's a time lag, a very well-defined time lag. At the same time, you've got this metamorphism, you've got generation of granites. And these are very evolved granites, full of radioactive elements, like leucogranite and such. So what you've got is a major redistribution of elements in the crust. And this is not limited to the superprovince. This type of behavior has been observed in most old cratons that have been mapped and studied. I'll give you examples. Here, the Kalahari Craton, which is South Africa and the Limpopo Belt, the Yilgarn Craton, Australia, and the Lewisian, the North Atlantic Craton. That's where we studied the rum intrusion, but of course the rum is much younger. So this is something which is not local anomaly. This is something which seems to always occur in cratons after they've been assembled. So to find out exactly what's going on, we need to find temperatures. So to find temperatures, we need to find heat production. So the temperature, structure, and evolution of crust rocks depend very much on their heat production. They contain radioactive elements. How can we find it? The difficulty, of course, is to find how much there is throughout the whole crust. And what we have, of course, on the outcrop is usually a shallow part, and it's very much harder to find out what's below. So geochemical sampling can't do the trick. So what we've done is measure heat flow. So when you measure heat flow at the surface, what you get is the total heat that leaves the Earth. And there's two major components. One is the heat flow that comes from the mantle. That's called the Moreau heat flux for simplicity. So that's the heat that's supplied from the convecting mantle that goes through the lithosphere, and that's brought to the base of the crust. That's something which comes from outside. And then we have the heat production within the crust itself. So we have the sum of these two components. The interesting thing is that if you're able to determine this one, then you see the whole crustal assemblage down to the lower crust, even though the lower crust is not available for local studies because it's just not on the outcrop. And so it's also interesting for a geochemical point of view because that's a strong indicator of what is the bulk composition of the crust in this Indian area. And the important thing is that also we have a link between the chemical petrochemical structure and the thermal structure. If I know this, I will know what temperature is. So there's a link between the type of crust that you form and the type of thermal regime that you get. And so what we do is that we measure heat flux at the surface, and then we find constraints on the mantle heat flux in many different ways. We can discuss them later if you're interested. We have continuous data from the mantle below, which give us good clues about the thermal gradient and the heat flux through the mantle. We also have seismic data. We know how thick the lithosphere is, and we have some internal systematics of heat flow. If we measure these two things, then of course we get this, and that's what we've been doing. just the super, so I spent about 30 years of my life logging heat flow, in the super, most of these data points are ours. It is a very boring thing to do because you sit on a borehole for a couple of days and you measure temperature every 10 minutes or so. Now, of course, the deeper the borehole, the longer it takes. And then that's the reasonably easy part, although you have bears coming in sometimes, but the hard part is to measure conductivity, and that's a very boring part. So there's only so much you can do without getting too bored. But anyway, throughout my life, I logged about 200 wells. Now, 200 wells may not seem a lot, but these are 200 kilometer deep wells. So this is quite a bit of anyway, so that's the map of let's see, there's a difference between the core and the belt. You can see there's a major difference between the belts and the core. We'll look at the statistics. It's very hard to get measurements up north, but we got sufficient to be sure that we do have a difference. And if you look at the statistics, the Creighton core has got this heat flux here. The numbers don't matter as much as their differences. The Creighton core is about 29. That's very low in comparison to most other places of heat flux in either continents and sunny oceans. If you look at the volcanic plutonic belts, you have 3 belts where we have enough data. And what is quite fascinating is that you can see, now we have lots of data points, so these are very robust things. You can see how close to one another these estimates are. So this also brings confidence that what we have is something which is always repeated. These are belts that were formed quite close in time, and you form basically the same type of crustal assemblage. These numbers are very close to one another. So it's a remarkable uniformity of cross-building mechanisms there. So what happens to temperature? So the interesting thing is that if we make a thermal model, we can split temperature in 2 different components. One is the relaxation of the initial thermal structure at the end of the crust building phase. We start with some crust, which has some thermal structure. We don't know it very well. I'll discuss that later on. But this thing will decay because we've stopped putting material to the crust, we've stopped perturbing the crust, and then we leave it on its own, and it will evolve. And the only thing that will change is that the heat production starts to kick in. And so we can split the temperature in 2 different components. One is the relaxation of its initial structure, and the second one is the heat producing component. They have different boundary conditions. So I will show you one example of what goes on. And the model parameters that we don't know the initial thermal structure, but we can parameterize it and investigate all the possibilities. Depending on the way the crust is built, there's going to be some crustal anomaly, and there's going to also be a lithospheric one if the lithosphere is thick or thick, etc. And that would be the steady state structure. And so that we can vary. And then we do carry out the thermal calculation. So I'll give you one example. We have a thin initial thermal anomaly. So the things will cool very rapidly and no lithospheric thinning. So what you have, this first component of temperature is the relaxation of the initial structure. And I'm showing you temperatures in the lower crust, just above the morro, basically the depth of point H, big H, where H is the depth of the morro. And tiny here is in dimensionless coordinates, but if the crust is 50 kilometers thick, then 1 is 100 million years. That's easy to remember, so that would be 50 million years and 100 million years here. Temperature is in degrees Celsius, so that's the temperature that's in real values, because that's the one we want to understand to compare with the theoretical evidence. Now the second component is the crustal reproduction. It starts at 0, because initially we just took the initial thermal structure and then we let heat production kick in. So of course it will increase. And you can see that it increases much more slowly than the decay of the initial structure. And that is something that's quite obvious because of course everything is in a crust that's losing heat to the atmosphere above. And so this heat loss accelerates the cooling and slows down the heating. So this is basically why these 2 curves occur on very different time scales. And of course, when you sum up the 2, this is what you've got, the sum of these 2. And you will notice that there will always be an initial cooling phase after crust building, and then it will heat up. for this particular calculation, the delay between the initial temperature here at that particular depth in the crust and the time at which you go back to this same value is about 60 million years. And of course, this is about the temperature of the high temperature metamorphism that we see. So you see these type of calculations show that there's going to be indeed a late phase of temperature increase in the crust, which is unrelated to anything external. It's solely the crust with its heat production that will undergo this late heating phase. At these temperatures, you will melt most of the rocks that are in the crust, and you will generate these granites that we see at the top. You can see that the crust in this particular area is able to go through a two-phase evolution. One is the initial crust building phase, but then there's going to be a later phase because you have crust which is quite rich in radioactive elements, and this crust is not stable thermally, and it will segregate most of its evolved melt to the surface. So that's conclusion on number 2. So the newborn crust of the superplanet was chemically involved when it got formed, and it had a high internal reproduction rate. That, of course, is something that we were expecting if we lose the mafic cumulates. And we know that because it was hot, it had to allow the delamination of mafic cumulates. That's why we started with this crust which was rich in radioactive elements. And then when it evolved, it started to cool down, but then it started to heat up again because of its radioactive elements. And the time lag is depending on the initial thermal structure, something that goes between 20 and 60 million years, which is consistent with the evidence actually needed. And the last thing is that the post-orogenic melting of the crust and the magma migration to shallow depths generate a stratified crust, quite close to what we see today. It's crust that is colder, because if you put all your radioactive elements at the top, then they're no longer at the bottom, so the crust will cool down because of that. And because it's cold, then it's also stable. And I think this is also one major reason why the continents that are from this way are stable, because they're cold. If they were not able to segregate most of the radioactive elements of the crust, they would be hot and they would be deformed by tectonic events. But no, they were able to generate their own stratification on their own, and this is why they are strong mechanically. So that's basically the story of the work that I've done on the crust. As you can see, there's missing points, but I think I've shown you that if you want to tackle a problem like this, it's important to look at the chemical evidence, but that's always going to be local. But then you have to look at the larger scale evidence, which is geological, and to bridge the gap between the two, you'll have to look at a set of physical processes. And if you are able to bridge the gap between these different aspects, then you make sense. And that's, I think, the message I would like to get across to you. So, thank you very much. Claude.
If you need to go to your business, go. We realize that today's ceremony took time longer than the normal seminar, but we have a chance now to address questions that might arise. So we'll start with Monty.
Just one, I have a comment which is leading actually to talk to Ben-tור. Ben-tור was working on the history of the Arabian Nobel Shield, which I think is the best example of a very well exposed and juvenile object. So all these stages that you showed of the superior actually appear in the Arabian Nobel Shield. Ben-tור mentioned another step. It was a very important one. It was the initial step. The initial step was the formation of what he called oceanic basalts, and later we said that these are oceanic plateaus. So actually this is a major part in the stabilization of the continent and in the formation of the oceanic plateau. Because the oceanic plateau is a massive feature, which is made mainly of tolites, and the basaltic of basalts and tolites. And therefore, it cannot be subducted, first of all, but also it's stabilized with the continent. But I want also to connect it to your last sentences, because then, you know, if you think about about this solid, about oceanic plateau. Then the uranium, thorium, and potassium in the oceanic plateau is much lower than the granite which are formed later. So then there is an issue.
No, as I said, I didn't talk about the core. So
this was related more probably to your core.
yes, that's what I mean. And so the core is, as you saw, is a low heat flow, and so it's definitely made of material which is not as rich in uranium and thorium as the accreted belts. So I didn't work on the core except for the heat flow. I know there's a bit of a debate. So some people have proposed an oceanic plateau, which is maybe linked to a big plume or whatever. So that's the core, I think. And indeed, if you don't have the core, you have nothing to accrete to. It's not clear that you would be able to have these belts colliding against one another if you had in the core. So I didn't mention that, but I did work on the core. There's interesting, you can also see why it's stronger. And well, I don't have the slides here, but basically what you find is that the core does not deform. You've got all the accreted belts, all the thrusting goes on in the accreted belts, but the thrust stop at the Earth's core boundary. Even more interestingly, the core now, because of its heat flow, is still stronger than the accreted belts. And so, for example, if you look at the mid-continental rift went on close to that, and it's something which propagated, and it never made it to the core. It made it through the belts, but not to the core. So obviously, there's still a strength difference there. So there's a major difference between the core and the belts. And so I think the only way we can explain this difference is by different type of origin. And indeed, I think the oceanic plateau is one of the favorite. The geochemists disagree. I think the main problem with the Earth's core, as I mentioned here in the Superior Province, is that there's not a lot of geological outcrops. So probably is a better place. But this is what I've been working on. So
here we have the desert, so we see everything.
Yeah.
So we have for that three as well.
Okay. In your talk, you treated mostly the crust. And what about the subcontinental lithosphere? What's its role in this process?
Well, I also work on the continental sphere, but I have less to say because it's not. Well, of course, it's important that you have the lithosphere, but I think the important thing is that two different things about the lithosphere. Thermally, it's linked to the crust. If the crust is hot, the lithosphere will be hot also. If the crust is cold, the lithosphere will be cold also. So there's a link between the two, and you can't just separate between the two. But there's a big time lag between what happens to the lithosphere and to the crust. So if you make, for example, if you put a lot of radioactive stuff on top of oceanic lithosphere, let's say, then it will take a lot of time for this lithosphere to be equilibrating with the crust above. You simply have to propagate the heat downwards. And so they're linked eventually, but they're not linked initially. And so there is some scope. For example, I didn't mention that, but one of the things we can say in the Superior Province is that given the short time lag, which is shorter than the calculation I've shown you between the end of the crust building phase and the late accretion phase, the best way to account for this is to have an initial lithosphere which is quite thick. So the thickness of the lithosphere is an important phenomenon, and we only see it through the transients in this type of analysis. In the talk that will be given tomorrow, I'll talk more about the lithosphere, and I don't want to give you, but that's important. I think you have to figure out how do you relate the formation of the lithosphere, which is also made of buoyant material, how do you relate it to the geothermal, the local thermal conditions. And but there's an interesting interplay between the crust and the lithosphere, and there's a lot of things to be done on this particular topic, I think.
Sweet. I want to ask you about the core. We see it at the present level of exposure. Actually, when the crust was generated, I assume there was some overburden on that. And therefore, what do we know about the heating conditions registered by the core at the time of its formation? What is the degree of metamorphism? At what depth did it occur? And well, that would be the starting point for discussion.
No, there's not been a lot of erosion because you have in this particular area. This is what we call people call the Physique kind of sedimentary assemblage. What you have is is a sedimentary rock that got sandwiched. So you can, I don't remember exactly the metamorphism, but there's metamorphic evidence in the sedimentary rocks that are reasonably shallow. So there was not much more than a few kilometers of overburden that we lost, because we still have slivers of shallow sedimentary rock. Even people are still able, for example, to reconstruct deltas, fans, etc., because the sedimentary evidence is still there. So you had sedimentary packages that are gone. Some of them got sandwiched in between volcanics in the deformation.
And they are 2.6, 2.7 billion years old.
The sedimentary rocks, no, because the core, of course, is older. And so basically you have a whole history of sedimentation and also erosion in the Earth's core that generated these fans that produce these shallow sedimentary packages before the accretion. So you do have this evidence, and so there's not a lot of erosion that's been going on in this space. So I think I have to check my sources because I don't remember this shallow, but yeah, there is evidence, and there was not a lot of erosion because you still have the sedimentary packages.
So, and this is something, but why does the heat production in the crust decreases with time? Shouldn't the amount of heat production elements decrease?
Yes, I didn't show the full thing. If you start, I'd split the temperature field in two different components. So basically you start with your initial temperature structure, and you can always do this, and you say, okay, I start my initial temperature structure, and then I include the heat production, okay? So the heat production will start heating the crust, but of course as it heats up, then the radioactive elements decay. So I didn't show the late phase. Remember what I've shown is 100 million years. So over 100 million years, it just takes time to heat up the crust by the radioactive elements. That's what I've shown you. And then if I would show you the later, I'll give you a very nice paper that I wrote about this. And then of course over billions of years, then you have the heat production that decays, because of course the radioactive elements decay. But over 100 million years, you don't see this.
So it's the amount of heat which is accumulating, not the amount of
It is the amount of heat. It's the amount of heat that's generated by the crust. Interestingly enough, if you compare, for example, these radioactive elements, how they can heat up the crust, and for example, you compare this with, you say, let's put basalt in a crust, you'll find that with these rates of heat production, you input as much heat as a big fat basalt per unit volume, it's the same thing, in about 50 million years. So in about 50 million years, these radioactive elements will bring to the crust as much heat as a basaltic intrusion. So there's an initial phase in which the crust will react to its radioactive elements, so it heats up. Then of course the radioactive elements decay, and so there's a long-term decay on top of that. I answered your question. In fact, there's an interesting delay between the lithosphere and the crust, because of course your radioactive elements will have to heat up the lithosphere. That's what I was mentioning to Oded, and that is occurring on a much longer time scale. And by the time you heat up the lithosphere, your radioactive elements have decayed away. So there's a nice.
I'm curious. Granite, we say always viscosity is controlled by quartz.
Yeah.
Your quartzite is much more viscous than the granite. The quartzite is more viscous.
Well, I'm not sure what the granite composition was used. I took this from what's usually referenced. I don't know exactly what the granite thinks. Obviously, it's not controlled by quartz, but that's the only thing I can say. You see, there was diorite. Diorite is not a granite, but it's not that far from granite. So, you know, it's just. The point I wanted to say is that you can use, you see there was a difference, you can, we don't know, I think, the crust topology very well. That's a major, and that's the point.
I was asking about the viscosity. On the first part of the talk, we were talking about crystallization of mafic minerals.
Yeah.
So, the question is whether the strongest connection between temperature and viscosity should be through the crystallization, because there is a no change in viscosity depends on the crystal content. And this process could be chopped, subdued, or so. We increase slightly the crystal content.
Yes, so I mean, these models, we are not able to do the full thing yet, but I think The major thing is that if you look, for example, at the rheology of, say, an olivine cumulate, I can tell you, it's still going to be flowing easier than a granite type thing. Okay? And so the main thing is that the higher temperature will be in the intrusion itself, so the colder temperatures will be in the country rock, and so the main resisting force on deformation is in the colder country rock. And so you have a viscosity ratio that comes in, but I think by and large you're controlled by the most viscous part of the system, and the most viscous part of the system is the surrounding rock.
If we got more questions, I had another common connection that we have with Bento. That once Claude was giving a talk, and he asked me if there's any references that I know about Bible and geology. So I referred it to what I think is Bento's last paper.
In the negative? The negative, yeah.
And the negative and storm and other examples. So it's a long process. Thank you.
Merci.